Hello everyone, welcome back to my channel. I am Bhagyashree, studying BE first year at Sri Venkateshwara College of Engineering, Bangalore. Today I am here with a new topic, bisection and Lagrange's inverse interpolation method. Now let's see the introduction to bisection method. In mathematics, the bisection method is used to find the root of a polynomial function. For further processing, it bisects the interval and then selects a subinterval in which the root must lie, and solution is iteratively reached by narrowing down the values after guessing, which encloses the actual solution. In this method, the interval distance between initial values is treated as a line segment. It then successively divides the interval in half and replaces one endpoint with the midpoint so that the root is bracketed. This method is based on the intermediate value theorem and is very simple, robust, and easy to implement. There are various names given to this method, such as the interval halving method, the binary search method, the dichotomy method, and Bolzano's method. Finding root by bisection method. As stated above, the bisection program is a root finding method that we often come across while dealing with numerical analysis. It is also known as the bisection method, numerical analysis. It is based on Bolzano's theorem for continuous function. So let us understand what is Bolzano's theorem. Bolzano's theorem. If on an interval a, b and f of a into f of b less than 0, a function f of x is found to be continuous, then there exists a value c such that c is belongs to a or a and b, or which f of c equal to 0. The bisection method problems can be solved by using the bisection method formula to find value of c of the function f of x that crosses the x-axis. In this case, the value is c is an approximate value of an root of the function of f of x. In this bisection method program, the value of the tolerance we set for algorithm determines the value of c where it gets the real root. One such bisection method is explained below procedure. Now let us see the bisection method procedure. Step 1. Choose two values a and b such that f of a is greater than 0 and f of b is less than 0. Step 2. Calculate a midpoint c as the arithmetic mean between a and b such that c equal to a plus b divided by 2. This is called interval halving. Step 3. Evaluate the function f for the value of c. Step 4. The root of the function is found only if the value of f of c equal to 0. Step 5. If c not equal to 0, then we need to check the sign. We replace a with c if f of c has the same sign as f of a, and we keep the same value for b. We replace b with c if f of c has the same sign as f of b, and we keep the same value for a. To get the right value with the new value of a or b, we go back step 2 and recalculate c. Now let us see the advantages of bisection method. Guaranteed convergence. The bracketing approach is known as bisection method, and it always non-convergent. Errors can be managed. Increasing the number of iterations in the bisection method always results in a more accurate root. Does not demand complicated calculations. There are no complicated calculations required when using the bisection method. To use the bisection method, we only need to take an average of two values. Error bound in guaranteed. There is a guaranteed error bound in this technique, and it reduces with each repetition. Each cycle reduces the error bound by 12%. The bisection method is simple and straightforward to program on a computer. In the case of several roots, the bisection procedure is quick. The disadvantages of bisection methods are, although the bisection method's convergence is guaranteed, it is often slow. So choosing a guess that is close to the root may necessitate numerous iterations to converge. Some equations root cannot be found because there are no bracketing values like f of x equal to x square. Its rate of convergence is linear. It is incapable of determining complex roots. If the guess interval contains discontinuities, it cannot be used. It cannot be applied over an interval where the function returns value of the same sign. Now let us see the introduction about Lagrange's inverse interpolation. Lagrange's inverse interpolation is the numerical method used to approximate the inverse of a function when the original inverse is either difficult to compute analytically or unavailable. This technique is an extension of Lagrange interpolation, which is used to approximate a function based on a set of data points. In Lagrange's inverse interpolation, the roles of the independent and dependent variables are reversed, aiming to find an approximation for the inverse function. The primary motivation behind Lagrange's inverse interpolation is to provide a practical approach to obtaining the of a function when direct inversion is not feasible or when the function is represented by a complex mathematical model. The primary motivation behind Lagrange's inverse interpolation is to provide a practical approach to obtaining the inverse of a function when direct inversion is not feasible or when the function is represented by a complex mathematical model. This method is particularly useful in fields such as engineering, physics, economics, and other scientific disciplines where understanding and utilizing the inverse relationship between variables is crucial. Lagrange's inverse interpolation involves constructing and interpolating polynomial that passes through a given set of data points. These data points are typically obtained from the original function. The interpolating polynomial is then used to approximate the inverse of the function by swapping the roles of the independent and dependent variables. Here are some key points of Lagrange's inverse interpolation. Purpose. Lagrange's inverse interpolation is used to find an approximation for the inverse of a given function when the function itself is not easily invertible or not known analytically. Input data. The method requires a set of data points x, y, where x represents the independent variable and y represents the corresponding dependent variable. These points are assumed to be taken from the original function. Interpolating polynomial. Similar to standard Lagrange interpolation, Lagrange's inverse interpolation constructs a polynomial that passes through a given data points. This polynomial is then used to approximate the inverse of the function. Caveats and construction. Lagrange's inverse interpolation not work well in cases where original function has completed behavior, multiple branches, or regions of rapid change. It is also sensitive to choice of data points and can introduce errors in regions with sparse or irregular data. Limitations. The accuracy of the inverse approximation heavily depends on the choice of data points and degree of the interpolating polynomial. Higher degree polynomials might introduce oscillations or inaccuracies, so careful selection is important. Alternatives. In cases where the function can be analytically inverted, it's generally preferable to use exact analytical inverse. Numerical methods like Newton-Raphson iteration can also be used to approximate inverse of a functions. Application. Lagrange's inverse interpolation can be used in various fields such as numerical analysis, scientific computing, and engineering, where the inverse of a function needs to be approximated for specific calculations. Advantages of Lagrange's inverse interpolation. Approximate inverse. Lagrange's inverse interpolation provides a way to approximate the inverse of a function when the original inverse is difficult to find analytically or numerically. This can be particularly valuable in scientific situations where the original function is complex, lacks a known analytical inverse, or is computationally expensive to invert. Numerical solution. Lagrange's inverse interpolation is a numerical method, making it suitable for cases where direct analytical solutions are not feasible or involve high computational complexity. It provides a practical way to handle functions that are not easily manipulable mathematically. Interpolation flexibility. The method is based on polynomial interpolation, which allows for flexible representation of the inverse function within the given data points. By adjusting the degree of the polynomial, you can control the trade-off between accuracy and simplicity of the approximation. Interpolation visualization. Lagrange's inverse interpolation helps visualize and approximate inverse behavior of a function using polynomial curves. This can add in understanding and analyzing the behavior of the original function and its inverse. Multivariate applications. Lagrange's inverse interpolation can be extended to handle multivariate functions, providing a way to approximate the inverse behavior of functions with multiple variables. The disadvantages of Lagrange's inverse interpolations are sensitive data points. The accuracy of Lagrange's inverse interpolation heavily depends on the choice and distribution of data points. Poorly chosen data points can lead to significant errors and inaccuracies in the inverse approximation. Runge's phenomenon. Just like Lagrange interpolation, Lagrange's inverse interpolation can suffer from Runge's phenomenon, where using high-degree polynomials to approximate the inverse function can lead to oscillations and instability, especially near the edges of the data range. Limited extrapolation. Lagrange's inverse interpolation is primarily designed for interpolation within the range of the given data points. Extrapolation beyond the range of the data can lead to unreliable results and introduce large errors. Unequiness and continuity. Lagrange's inverse interpolation assumes to inverse function is well behaved, continuous, and has a unique inverse within the range of data. For functions that have multiple branches, discontinuities, or complex behavior, the method may not provide accurate results. Degenerate data. In cases where data points are closely clustered or nearly aligned, Lagrange's inverse interpolation can exhibit instability and inaccuracies, leading to poorly conditioned interpolating polynomials. High-degree polynomials, where higher degree polynomials can potentially provide better accuracy than can also introduce numerical instability and overfitting to the data, resulting in unrealistic behavior to the approximate inverse function. Computational complexity. As the degree of the interpolating polynomial increases and the computational complexity of Lagrange's inverse interpolation also increases. This can lead to performance issue, especially for large datasets or complex functions. Thank you for watching.